Hello everyone, welcome to another episode from Chedexcel. Today we are going to talk to you about atomic structure and the periodic table. This is the second chapter of Unit 1. So, we will see what are the basic stuff you have to know about the atomic structure, and then how we are going to find the molar mass or the relative atomic mass using mass spectrometer, and then we are going to talk to you about the existing of electrons, about the subshells and orbitals and stuff. And then we are going to talk about the periodic table and the periodicity, that means the periodic patterns, which means we are going to talk about atomic radius, ionic radius, first ionization energy, successive ionization energy, electronegativity, melting point variation. So, that is the whole content, and whole content I will be doing with 6 videos here, 6 parts. First part I am talking about today, we are going to talk about the atomic structure and the mass spectrometer. Then the next video we are going to talk about how to interpret or how to draw the mass spectra of bromine and chlorine, and then we are talking about existence of electrons and how to write the electronic configurations. Then we are going to talk about the periodic table. Then 5th and 6th we are going to talk about the periodicity, where the first video I am going to talk about atomic radius, ionic radius and first ionization energy. Second video I am going to talk about successive ionization energy, melting point variation and the electronegativity. Sometimes I might do the successive ionization energy and the first ionization energy in one video. Anyway, we will see. Right, to begin with, from grade 7-8 onwards, you might know that anything around us which has a mass and occupy a volume is called as matter, and matter is made of subatomic atoms. An atom is made of 3 subatomic particles. That is the beginning of this chapter. So, you have certain stuff. So, I just draw like this. Here we call it as nucleus, and around the nucleus we have electronic shells. Okay. Roughly I will draw this, and in electronic shells we have electrons. So, E means electrons, and this is, let us say, proton, and the other ones are neutrons. These are very common, very basic stuff that you should know by now. So, the number of protons present in an atom is called as the atomic number. The number of protons and neutrons present in an atom is called as the mass number. Number of protons and electrons are the same for a given neutral atom. They remove electrons to form positive ions, they gain electrons to form negative ions, and the number of electrons they remove or gain depends on their electronic configuration. We will talk about it later. And the nucleus is positively charged, and compared to the size of a nucleus, compared to the size of the atom, the size of nucleus is very, very small, because it is very tiny dot, right. So, there are different examples people have used to explain the size of a nucleus compared to the size of an atom. Even an atom is also so small. One example is, if the nucleus is the goalkeeper of a football goal post, the gap between the goal post and the one goal post and the goalkeeper is 30 kilometers. Huge. The whole idea is, compared to the size of an atom, the nucleus is so small. So, you have empty spaces there, but we all have certain structure, right. We all have a body, we can feel it. How come that happen if an atom is so small? That is because there are millions of trillions of atoms are used to give our structure. But if you just take one atom, it is negligible, you can't see anything. I can give you another example. Let us say you have a picture, normal I will say 6 feet and 4 feet picture frame, and you are dividing it into 1 millimeter small squares, and you enlarge that 1 millimeter to the 6 feet to 4 feet. You won't be able to see anything. In fact, if you just have 1 millimeter squares of a 6 feet 4 feet, I am just taking this stuff as example, you won't see any picture of this 1 millimeter square. So that's the thing, one atom is almost impossible to see. Actually, to date, no one has seen an atom. We assume that this would be like that. Anyway, so those are not that much. What you have to know is basically to fill a small table. So one part is subatomic particle here, and you have relative mass and relative charge. I am erasing this as well, relative charge. First one is proton, relative mass is 1, relative charge is plus. Then neutrons, relative mass is 1, charge is 0. Then electron, relative mass is 1 over 1836, or you can say 1 over 1837, this is minus. Actually, even though we consider as protons and neutrons have the same weight, neutron is slightly heavier than proton. So that's the reason why you get either 1836 with respect to protons, 1837 with respect to neutrons. Anyway, those are the basic things you have to remember. Now, when we go to the next part, some elements have isotopes. It's a very common thing they ask in Unit 1. What are isotopes? Isotopes are different atoms of the same element with the same number of protons but different number of neutrons. So when someone asks you to define isotopes, this is a very common question in Unit 1. Isotopes are different atoms of the same element with the same number of protons but different number of neutrons. You can say different atoms of the same element, the same mass same atomic number but different mass number. Commonly they ask you to interpret it subatomic particles. So we had to do it with that. Now isotopes have different mass numbers so that their mass is different, but isotopes doesn't have different chemical properties because isotopes also have the same number of electrons. So they have the same chemical properties, but their physical properties such as density, mass, volume will also be the same. Density, mass, those stuff would be different, very slight different. So isotopes have similar chemical properties. Why? Because they have same number of electrons. To find out these isotopes and using the isotopes their percentage, we had to find the relative atomic mass, and to find that relative atomic mass we use a machine called mass spectrometer. So today we are going to talk about that as well. So before that, we will see how to find the relative atomic mass of an atom using the isotopes. So what you have to do is, let's say it's a very common one, chlorine 35 with 75%, chlorine 37 is with 25%. So relative atomic mass, or we say RAM value, 35 into 75 plus 37 into 25 divided by 100, you get it as 35.5. That's how we find the relative atomic mass, right? It's a very common one. Another example, potassium, RAM value is 39.1. Potassium has 39 and potassium 41. You are asking what are the percentage abundance for each, potassium 39 and potassium 41. So we can take this and another example, it's very common one. They have asked with potassium and copper in past papers. So potassium 39 you can take it as X, then potassium 41 is 100 minus X. Then you can do the same thing. We know the RAM value, 39.1 is equal to 39 into X plus 41 into 100 minus x divided by 100. You can find the x from here, you will get it as 95%. You can easily apply this one to the calculator and get it. So, like that questions have asked, but mainly they would ask this one with the relative atomic, the mass spectrometer. So, we will see how we can find or how we can discuss and then interpret the properties and the functions of the mass spectrometer. Right. So, the next part is mass spectrometer. So, normally you won't be asked to draw the mass spectrometer. So, here you have a small part. I am just drawing a rough sketch of this. Right. So, I am putting part A, B, C, D, E, F, G, right. So, this is the rough sketch of the mass spectrometer. We will see what happens with each part. Now, we have part A is called as the high temperature region. There is a place where we convert the solid or liquid atom or the sample into the gaseous state. So, capital A is a high temperature region. In that region, we convert solid or liquid into a gas state, because mass spectrometer we can only use gaseous substances. So, there is the place where we convert solid into a gas or solid or liquid into the gaseous state. Then B is ionization chamber. Right, ionization chamber. So, what happened in the ionization chamber is we bombard the high energy electrons with those gaseous atoms we formed from the high temperature region. So, bombardment of electrons with the gaseous atom, they ionize the atom. So, it will also remove an electron. So, once they ionize electrons, you get positive charge ions. Now, for example, let us say if I write it over here, if you have sodium, when sodium gas is bombarded with electrons, you get sodium plus gas, and total 2 electrons will be removed, this electron and another electron, or you can just write like this. Electron. That is the one thing. So, ionization can happen. The other thing is, let us say you have chlorine. If you have a chlorine, sometimes chlorine can remove one electron to form Cl2 plus, or sometimes it can break the chlorine bond to form Cl plus and Cl minus. So, they all are in the gaseous state. So, that is what happened in the ionization chamber. They form positive and negative ions if it breaks the bond. If not, it produces positive ions and electrons. So that's what happened in the ionization chamber. Part C is electric field. In electric field, we accelerate only the positive ions. We have a mechanism to accelerate only the positive ions. So we accelerate only the positive ions. Now inside the mass spectrometer, there is something called a velocity selector as well. So when we accelerate those particles, we allow them to reach to the same speed. Why? Because in part D, where we call it as magnetic field, right, where we call it as a magnetic field, only the deflection of those positive ions depend on their mass to charge ratio. Because if they have different speed, when you reach the deflection, the one which has a higher speed won't be able to deflect. So what happened in the magnetic field is, according to the Fleming's left hand rule, those accelerated positive ions are deflected, and that deflection depends on their mass to charge ratio. Normally we say m over z, mass to charge ratio. Higher the mass, smaller the charge. Usually this charge is +1, very rarely, but it's very common question they ask. Sometimes this positive ion can make +2 charge as well, removing another electron. So mass to charge ratio, if the mass to charge ratio is high, the deflection is low, right. So if I draw it over here, right, let us say here 2 particles reaches, let us say chlorine, this should be chlorine 37 plus, this is chlorine 35 plus. Higher the mass, lower the deflection. Lower the deflection means it does not tend to bend that much. So that is chlorine 37, this is chlorine 35. So that is what happened in the magnetic field. In the magnetic field, particles start to deflect according to their mass to charge ratio. Then we have E is a detector. So all the deflected particles will be detected by E. So this is our detector. And part F is amplifier. So sometimes, for example, these ions is not going to reach the detector. So what we do is we increase the magnetic field strength. So when we increase the magnetic field strength from the amplifier, this particle can also reach the detector. The ones that already been detected is no need to detect again. So they would bend even more. So they go and hit this wall. So that does not matter because we have already detected them. So amplifier will increase the magnetic field strength, and G is the recorder. So in the recorder we get the mass spectrum. The mass spectrum, the y axis would be the percentage abundance or relative abundance or the relative intensity, right. So if I draw it that part over here, roughly the y axis would be percentage abundance commonly or relative abundance, and the x axis is mass to charge ratio. So you get the peaks like these lines, you get lines. Always the furthest away peak is called as the molecular ion peak, because that gives the molar mass of the element or the molecule we tested. So furthest away peak is the molecular ion peak. That means that molecule hasn't broken from anywhere, and it has given the molecular ion peak. So we'll talk about the mass spectrum of chlorine and bromine in the next video. So this is the rough idea about what happens in the mass spectrometer. So you have the high temperature region, here you have the ionization chamber, electric field, magnetic field, detector, amplifier and recorder. So that's what happens in each of the section. So from the solid or liquid what we use to measure the mass spectrum, we can convert into the gaseous state, we can make into the ions by bombarding with electrons, we can accelerate it, we can deflect it, and we can record it. So we will see how we can do some questions regarding this as well, and we will interpret the mass spectra of chlorine and bromine in the next video. So today what we talk about is the basic part of the atomic structure and the mass spectrometer. If this is helpful, consider subscribing, and Thanks for watching.